Tom Speer is a great catch for us in this context. The man sails a 34-foot try that he keeps up in the Seattle area, in the Pacific Northwest anyway. And he was at one time a hobbyist in the world of boat design. To make a leap from being a hobbyist in the world of boat design to designing the wing for USA 17, the boat that won the America's Cup in 2010, the largest wing ever built, the wing that would not fit under the Golden Gate Bridge. Now that's quite a leap, except of course there was a parallel track that was professional that made it all make sense. For example, his first career was in the U.S. Air Force. He rose to the rank of lieutenant colonel. One of his titles in the U.S. Air Force, from 1990 to 1995, Flight Test Program Manager, Air Force Flight Test Center, Edwards Air Force Base. It occurs to me that what he could tell us about that would be a fascinating program. What he could not tell us would be really fascinating. 1995 to 1999, he served as Principal Engineer, Tier 3, Boeing Information Systems Defense and Space Group. He then went to a different part of Boeing. He was a technical fellow in the Flight Controls Research of Boeing Research and Technology. Along about the time that Oracle Racing began to think about putting a wing in their big trimaran, he became a consultant. He is now full-time with Oracle Team USA. It's a nice progression of events. It probably wasn't all that hard for Oracle to find him because Tom Speer keeps a personal website, tspeer.com, that is a lodestone for people who are interested in topics such as ventilation, inception of surface piercing, and submerged oils and stuff. If that's your thing, tspeer.com is highly recommended. He recently sailed the Van Isle 360 in his 34-foot try. And before I introduce him, I should let you know that there is no broadcast today of the racing. The TV broadcast begins tomorrow, so don't be confused if you don't get that. But I am so pleased to have Tom Speer here today. I first met him on a flatbed trailer on the tarmac at the New Jerusalem Airport. We were riding behind a pickup truck. We were chasing the first contraption, land sailor thingamajig. He's done a lot of land sailing too, by the way. The first machine ever to propel itself directly upwind using only the power of the wind faster than the wind. The same machine that 2 years ago went downwind faster than the wind using only the wind and as much as 3 times the wind. And if this tweaks your curiosity, come back on October 17 because we'll have the man here to tell us about that. Right now, a man of boundless curiosity and capabilities, a man who would show up at New Jerusalem and ride a flatbed trailer because maybe it was cool, and he would qualify it, if I tell you he's designing the AC-72 wing that Oracle is going to start load testing next Monday, he would qualify that. Say, oh, this guy is responsible for this, and this guy is responsible for that, and it's true. But I've seen the work description, and this is the man who's designing the wing. Welcome, Tom Speer.
That was quite an introduction. And a little bit of it may actually have been true. Okay, I think this may be a bit different talk than some of your luncheon talks, because I don't need to tell this group that the 34th match for the America's Cup is going to be held in San Francisco, or that it's going to be held in wing-sailed catamarans, or that the kind of racing they're going to do is completely different than they've ever done in the America's Cup before. You guys know all of that. So what I want to do is give perhaps a bit more technical talk than is usual, because we're always asked, just what is a wing sail? Why is it faster than a soft sail rig? And as sailors, I'm sure you want to know how these things are operated and what it's like to sail a wing sail. So that's what I'm going to cover today. I want to go through kind of the history of where they came from, talk a bit about the control system and the aerodynamics of the wing sail, and then kind of wrap it up with the sailor's view of the wing. So you can't talk about the history of wing sails without going into basically what is a wing sail to begin with. Well, I like this picture because there's 160 years of sailing technology in one shot. In the foreground is the America, which is a replica of which is tied up here at the Golden Gate Yacht Club. And of course, back then, all the masts were fixed round masts, and they had fabric mainsails. One of the advantages of the America was their cotton sails compared to the linen sails of our competitors. But then, really, with the advent of the smaller multi-hulls, the beach cats and so forth, but also with the scow classes in the Midwest and probably some others, we saw rotating masts come in with full batten sails, and these allowed better shape control and higher aspect ratio rigs. And now what we've done is we've taken the wing mast kind of to its logical conclusion, where it became bigger and bigger until it's now the entire sail area, and there isn't any sail left. Now the C-class cats is really where the wing sail came from. Back in the early 60s, the C-class catamarans had conventional sloop rigs. And what you're showing in this diagram, here is the rig, and then this is like a cross-section cut sloop rig for each one of these. So with a sloop rig, you basically have the mast, the mainsail, and the jib ahead of it. And then they went to basically taller cat rig, unit rigs. And then the mast grew in size to be as much as 30% of the total sail area. And then in the late 60s and early 70s, they started trying to see if they could make it more like an airplane wing. And they were experimenting with basically a single piece wing that could be distorted to sail on both tacks. And then the real breakthrough came in the late 60s, where they went to rigid wings that were comprised of a number of symmetrical airfoils in tandem that, when they were deflected, formed slots. And so these form slotted flaps just like you see on an airliner when it's landing. When you look out and see those, the wings sort of fall apart into a whole bunch of different pieces. That's what the wing is like on these C-class catamarans. And an Australian boat, Miss Nilax, was the first to compete with a rigid wing of this kind. And they got fairly complicated with with two slots and all kinds of pieces and complex control systems. And then in the late 80s to the present time, the rigs have basically gotten cleaner, simpler, and taller yet. So here's a picture of the Edge 3, one of the later of the Australian wing sails from that first period of wings. And you can see the two slots formed by the three elements of the wing. And on the right is a close-up of the control system, which is just incredible. All kinds of pulleys and wires and levers. Very complex, difficult to tune, and of course very prone to breaking. And these are what the modern cats look like. Kagato was really the first of the modern generation. She was the first one that could twist the main element. So the main front part of the wing there could be twisted, and not just the flaps. And the smooth twist up and down the span of her wing was a major performance advantage. And then just recently, you had these other cats all competing for the C-Class championship. Invictus is a British design, probably I think the latest of all of these. Patient Lady 6 is the end of a long line of patient ladies that were started by Tony DeMauro and designed by Duncan McLean and Dave Hubbard on the East Coast. And Canaan is the current holder of the C-Class championship. She's a Canadian boat. And Alpha is a little bit older Canadian boat that first won the championship from the United States and brought it to Canada. America's Cup has seen wing sails twice in its history. The first was in 1988 when Dennis Conner defended with the wing sail catamaran. They built two cats, shown in the left picture, one with a soft sail rig, one with a wing sail. And even after the soft sail rig had been sailed and tuned and developed for a while, the wing sail, when it started sailing, was faster right out of the box. And so, because it was a faster boat, that's the one they defended with, and defended against the New Zealand big boat, KZ-1, shown in the second picture, and was able to win that one very handily off San Diego. And then in 2010, as Kimball mentioned, USA 17, sporting the largest single wing ever built. That wing is longer than a 747 wing tip to tip and bigger than one side of an A380, which is the world's largest airliner. And that won against Lingy 5, shown in the fourth picture there, an equally giant catamaran off of Valencia, Spain. So how does a wing sail control? Because this is really, I think, one of the key differences between a hard sail and a soft sail. So here we're looking down on an AC-45, matter of fact, one of the very boats that are going to be sailing out here this afternoon, and kind of getting the helicopter's eye view of this. In the front is the main element. The main element basically does the same role as the mast, and it also carries most of the lift. Behind the main element are the flaps, and these are hinged just ahead of the main element trailing edge so that they form a slot when deflected. And the flaps are divided into several segments up and down the span because that makes it easier to assemble the wing, and also they're individually controlled to control the twist. So these flaps each have a control arm that you can see the blow up in the center there, with cables that run to the main spar and then down the main spar to the bottom, where they go to the main control arm, which is attached to the flap at the bottom. And so these cables running up and down the main spar transmit the loads from the flaps to the spar, and you don't have to have the high tension running along the leech that you do with the soft sail in order to control the twist. And then finally, the entire wing is rotated with what we call the traveler. It's really at the sheet. And the wing sits on a ball, just like on a Hobie cat, and the whole thing is rotated by the traveler. Because there isn't the high tension that you have with the main sheet, and the traveler is just horizontal, it's very lightly loaded. Even on USA 17, it was just a 2-to-1 purchase to a fairly modest winch, and it's only a single purchase on the AC-45. So it's very easy to trim these wings in and out, and that's the key to making them highly maneuverable, is that you can turn the power on and off in an instant. So if you take the wing and slice it horizontally, shown in the upper left, you basically get these two teardrop sections that are shown here. So we have the first one is the main element, and then the second one is the flap. And on some wings, there's a third piece that which we call the tab, which is like a plane flap that can be articulated between the main element and the flap. And you can see in the second diagram there how the slot is formed when the flap is deflected, And then the tab basically can regulate the size of that slot. Not all wing sails have a tab. USA 17 did not, and the AC 45s do not. But I expect that you'll see them on the AC 72s when those start sailing. So you have basically 4 controls to the wing. You have, or 3, excuse me. You have the traveler rotating the entire wing. You have the camber control, which controls the flap angle. And then you have twist, which is really the difference between the angles at the bottom and at the top. And so you can have twist in the flap, and you can have twist in the main element. And again, not all wings have the ability to twist the main element. The AC-45s do not, and USA 17 did not. You may or may not see twist in the AC-72s. I don't know what these wings look like this yet. So let's take a look at how the wing control system works. What I've shown is that same wing that we saw in the helicopter spots. And in this drawing, I've removed the frame so that you can see the main spar and the control arms on both sides. So at the bottom, you have the main control arm, and then at the end of each flap segment, you have that flap's control arm. Now the forces on the wing, you have the lift pushing sideways, and that is restrained by the ball and by the stays and by the traveler. And these are all basically pulling sideways on the wing at the edges. And as a result, the wing just naturally wants to fold in half. But it's prevented from folding in half because there is a control line from the center of the main control arm to the main element, and that limits how far it can rotate. So that's how we control the camber, is we simply regulate the length of that line. It just goes to a cleat, and the beauty is that it's self-tacking. When the forces reverse themselves to the other tack, the wing simply folds in the opposite direction, and the same setting on the camber control line limits the amount of rotation of the flap. Now, that basic controls the bottom flap. Linking the bottom with the other flaps are the control lines. So the control lines from each of the flap control arms go down the main spar and then back to the control arms on the main control arm. But the wrinkle here is that they cross over. And the result is that when the main control arm on the leeward side moves back, it pulls forward on the windward side control arms of all the other flaps. And likewise, on the windward side, when that main control arm moves forward, it feeds slack into each of the other flap control arms. So in this way, all of the flaps are slave to what happens at the bottom. And so that one camber control setting for the bottom flap really controls the camber up and down the entire span of the wing. Now here's what that looks like on the AC-45. We're looking at the bottom of the wing, and you can see this is the main control arm. Here's the flap, and this is the main element. And the camber control line goes from here to the main element, and these are the control lines for the various flap segments coming down the mast. Now, they don't actually end right here. Instead, they carry in to this sector, and that is the twist control. So what the twist control does is it basically, you can let it rotate, and it will feed slack into the upper control lines, controlling the top part of the flap, and let the flap twist off to leeward. And it's restrained by a control line right here. It works just like the camber control to limit how much it rotates. So you basically just have these very simple controls. You have the traveler, you have the camber, and you have twist. And that controls everything there is about the shape of that wing. And here's what it actually looks like in practice. Again, main control arm, the twist quadrant, the twist tackle is underneath here, and you can see the line here. And that's it. It's really quite simple and elegant. And this system, this approach, was basically developed by Dave Hubbard. So now let's talk about the aerodynamics of the wing and how these various controls contribute to the performance. So one of the surprising things about any sailboat is that the weight that's left by the rig is absolutely critical to the performance of the boat. So here we have an AC-45 sailing off wind. The apparent wind is ahead of the beam because the boat is sailing so fast. And the aerodynamic lift is, by definition, the component of the force that's at right angles to the apparent wind. Now, the lift is generated by the rig deflecting the wind to windward. And so it leaves this vortex sheet behind it, which is formed because the wing is only deflecting the wind over a finite span. So around the edges, the wind has to come in and replace the air that's been deflected. It's just like a giant canoe paddle pushing sideways, and you get the same sort of vortices around the edges of a canoe paddle. Now the effect of that, so here's what that actually looks like in real life. Right here is a Volvo 70 leaving Cape Town in a fog bank. And you can see the wake that's left by the boat and how this vortex rolls up. And the wake goes for miles behind the boat. It's really quite remarkable. Now, half of that deflection of the wind to windward is felt at the rig itself. And because of that, that deflection of the wind due to its own lift, it's as though it's had a local wind shift right at the wing. So you could say that the boat sails in a header of its own making. And so if you think about the lift as being right angles to that, it's rotated aft. And so in sort of the lift drag bookkeeping, this looks like you've added a drag component compared to the original lift. And we call that induced drag. And it is in fact the largest component of aerodynamic drag on the boat. And minimizing that is really what sail trim is all about. And that's why control of the twist is so important on these wings. So as designers, what we do is we take a look at how the wind is deflected in a plane that's perpendicular to the wake. And we use that knowledge to design the planform shape, the span, and the area of the wing. And then we have another plane that's a horizontal cut through the wing, and we use that to design the cross-section shape. So we take this complex three-dimensional design problem and we turn it into two much simpler two-dimensional design problems. And that's basically how we come up with the aerodynamic design for the wing and the sail. So here's what the two-dimensional section design looks like. Again, you've got the two teardrop shapes, main element and the flat. And on the left is a plot of the pressures around the wing. So the blue curve is the leeward side on the main element. The yellow is the leeward side on the flat. The magenta is windward side on the main element, and the red curve is windward side of the main element, and the magenta is the windward side of the flat. And the difference between those two, that area, represents the lift. You can see that most of the lift is carried by the main element, and most of it is concentrated near the leading edge. On the right, it shows the grid that we use to compute this, and the grid is fitted to the streamline. So those horizontal lines are parallel to the flow around it. And you can see here where the flow comes into the dividing point. And all this air goes around the lee side. All of this air goes around the windward side. There's a similar dividing point here on the flat. And all of the air here goes through the slot, and the air here goes to the windward side of the flat. And the final graph on the bottom left shows the distribution of the aerodynamic drag around the entire section. And you can see that there's very little drag on the windward side. Most of it is all on the windward side, and especially near the leading edge, which is why designing the leading edge and the condition of the leading edge is so important to the performance. Now, what I'd like to show is that the flow is not quite as smooth and steady as it looks. Here's a computational fluid dynamics calculation where we did it clear down on the scale of the turbulent eddies. And you can see that the turbulence that's shed off of the windward side going through the slot. And you can see the wake from the main element trailing over the flap and how the turbulence gets amplified as it goes over the flap. Here's basically the same thing from a little different view. You can see that the turbulence is not only unsteady in time, it also varies widely along the span of the wing. And so the real flow is quite complex. So let's compare the sections of the wing mast sail rig with the wing sail rig. Because if they had the same planform and the same twist, this is really the main difference between the two. So in black, we have the mast, rotating mast, and the mainsail. And then in red, we have the wing sail. And this is a typical shape with a tab that might be typical of, say, a C-class cat. And the mast and mainsail shape were from USA 17. So here is a plot of the lift and drag. On the left is plotted vertically the lift versus the drag. And on the right, the two curves are lift versus angle of attack. So you see there's quite a difference in performance between the two. There is an area where they have very comparable performance. But the big difference is that the wing sail rig has a much higher maximum lift, about a third more than the soft sail rig. It also has a minimum drag, and the beauty is that its minimum drag occurs at a lower lift and its best lift to drag ratio at a higher lift than the soft sail rig, which makes it a much more versatile rig. So you can see that there's only really a narrow range here where the soft sail rig is performing at its best, whereas the wing sail has a much broader groove. So it's a much more tolerant sail in terms of its performance. So that's really the key difference in terms of the section design between the soft sail and the rigid wing. And on the C-class, that's particularly devastating because they have a limited amount of sail area, and they can't put up additional sail for the downwind like we can with the other classes. But even without that, it's still a much better all-around rig than the soft sail because of its tolerance and its higher maximum lift. So here's what it looks like in three-dimensional computation. This shows the AC-45 sailing upwind at about 14 knots of wind. And the flow is attached pretty much everywhere on the wing and on the sail. There's a separation bubble right here on the windward side, just ahead of the trailing edge before the air goes through the slot. But that doesn't cause very much difference in drag. And at the bottom, you can see how the flow is already starting to head down and around the foot to roll up into the vortex at the bottom. But the really important part is the graph on the right. That shows the distribution of lift from top to bottom. And when you combine the wing with the soft sail jib, you get a nearly ideal shape to that lift distribution to minimize the drag for a given heeling moment. And so that's why the combination of the sail and the wing works so well on these boats. I'd like to show you what that looks like in three dimensions. Here we have basically a line of streak lines in a plane starting very near the water surface, and this is going to sweep up the rig, and you'll be able to see how the wake forms at different levels and kind of get an idea of what the airflow is like around the whole platform as well as the wing. Notice the distortion. Dagger board is raised. So, to put it all together, as a designer, what we're trying to do is we're trying to get maximum lift and minimum drag out of our wing. So the lift is limited largely by the heeling moment of the platform. Once you start flying that hull, you can't stand any more load on the wing, and you're basically capped. And my teammates are showing me up here. So just like that boat that sailed by, limited at how much moment you can stand. That's right. That's right. You like my visual aids here? And that's limited basically by the template in the AC-72 design rule. So we come down and we're basically limited in what we can do there. And the other thing that limits maximum lift, especially in light winds, is just aerodynamic stall. And that's largely a function of the section design, which, as you've seen, drives us to the slotted flap. And that's limited in the design rule by what's called the half-girth rule, which basically limits our ability to use things like follower flaps and other devices that would change the area of the wing. Now, minimum drag is, as I mentioned, the big thing is to minimize the induced drag. And the taller you make a rig, the less the induced drag will be. But that's, again, limited by the design rule. So what we basically have left is twist. And that's why we have the control system that we do, is to control that twist. Then the profile drag of the section is proportional wing area, again limited by the design rule, and the section shape. And here we have a little bit more freedom under the design rule, but we're still limited by the flap angle that the control system can create. And so probably the biggest difference in the wing design is whether or not we try for laminar flow in the boundary layer. Now, that is limited by the environment. For example, if you were to have water droplets all over the wing, they act as little roughness elements. And so if you're trying for laminar flow and you're sailing in the fog, you probably can't achieve it. But then again, I mean, how often would you see that? I mean, fog, San Francisco, chance in a million. So I kind of like to wrap it up by reiterating, why wing sails? Well, the aerodynamics are superior to the soft sail rig. You have higher maximum lift, and you have a lower drag, which allows you to point higher and go faster downwind. The control system gives you the precise control of the twist, so you can minimize that induced drag, and the precise control of the camber. So again, you can minimize the drag for all the lift ranges it's trying to sail in. And the structural loads are far lower than for a soft sail rig because you don't have that massive main sheet and bang tension. So that allows you to take weight out of the entire rest of the platform. And then finally, the instant on-off control of the power allows you to maneuver very adeptly. So you can take a 45-foot cat and take it around the buoys just like a beach cat. What I'd like to show you now is kind of the sailor's view of what it's like to sail.
This wing is identical to the wing we used for the last America's Cup. Today we're going to have a quick talk on how the wing works, what the wing is, and what it's made out of. Here we have a two-element wing, so it's got a fixed front element, which is the structural mast, and it's made out of carbon fiber. And back here we have the flaps. We have 3 flaps, 1, 2, and 3 from the bottom up. It's made out of carbon fiber back with a Kevlar nose cone. On every top of every flap there's a control arm. So the control arm 2, 3, 4, and the bottom control arm is this one here right at the bottom. That sets also the camber, which is the hinge point, which gives the camber all the power or deep power when you need it. Instead of a sail, the film has shrink wrap plastic, which is the same as you buy when you buy your meats in the supermarket. It's shrink wrapped on with sticky tape. Ours is black because we put paint on it. It is very strong this way, and it holds the pressure. But if you put a knife through it or something sharp, it will cut it instantly. We got 3 functions. The first one is camber. The second one is twist. And then we have the sheet. The camber is this white line. By easing this line, it allows the front element and the back element to get an offset, a camber. In general, we sail between 17 to 35 to 40 degrees of camber, so it's quite a big angle between the front and the back element. That gives the boat a lot of power, and depending on the angle of sail, we adjust it. Upwind to downwind, it's quite a big difference. If you get too much power, it allows us to ease this red line. By easing this red line, all these cables, this system here, which is underneath the wing, this triangle will move the lure and adjust all the cables and flaps above there. The 2 functions on the wing are sort of like a set and forget function, which you adjust more upwards and downwards. The other ones goes to this winch and is 1-to-1 onto the wing here. And that allows the wing to go in and out. As far as control system goes, they're all the same between the boats. The only option you have really is to play with paint pinches and see what you like best in terms of performance. I like it, it's a nice toy to play with.
That was Dirk de Ritter, the main wing trimmer on Oracle 4. So that's pretty much what I've got. I'd like to open it up for any questions you might have.
You have border seas coming off the top of the mast, and you have border seas at the bottom coming off.
Right.
Why don't you have a plate on the top to reduce the amount of border seas, both top and bottom?
Well, there are a couple reasons for that. One is under the AC72 design rule, there's only a very limited size of horizontal area that you can use for that. It's really not much more than you need for the control arms themselves. So we're basically not allowed to under the design rule. But as a more practical answer, putting a plate on will extend the effective span, but it's for the amount of area that you add, in other words, the amount of additional drag, it's never as effective as simply making the physical span longer. And so unless there's some other limit to the span, you're better off just making a taller rig.
Who sets up the design rules?
The design rules were originally created by ACEA, and they had Morelli and Melvin under contract that wrote sort of the first draft. And then after that, the revisions have all been voted on by the competitors. Initially, it required a majority vote, and now it requires a unanimous vote, but they can still change the design. Go ahead.
So we've seen 5 boats flip recently. What are the aerodynamics of flipping?
Well, it's really just like on any boat, it's the coupling between what's going on with the hull and the wing, or the, basically the rig.
What's the danger?
Yeah, the danger zone is, the worst is basically when you're turning downwind, because the boat is slow, it can get overpowered. Once it gets up to speed, then the boat's speed subtracts from the true wind, so the apparent wind actually goes down. But at that point, you have a problem because you can't let the wing out far enough to completely depower it, and if the hull digs in, then really it lifts the rudders out, so you're out of control, and the boat just pitch poles or rounds up and goes over the side. I think there was a question back here. Yes.
I was watching yesterday, when the boats tack, they really slow down. In fact, they almost stop. And with the 3-knot flood like today, how do they reaccelerate?
It's interesting, if you actually time attack, it takes about the same amount of time for these boats to tack as it does for, say, a Virgin 5 America's Cup boat. The difference is that they go into the tack doing 15 or 20 knots, and they slow down to maybe 10 knots during the tack, and then accelerate back out again. So while they spend the same amount of time turning and accelerating again, the difference in speed can be several knots. And so they do seem to lose a lot of speed, and it seems slower, but it's not actually slower. But basically, because the boats are very light, when they come into the wind, then they don't have as much inertia to keep them going through the tack. So the wind slows them down a lot more than it does on a monohull.
Do they fall into irons, though?
It looks like you only adjust the twist from something under the boom from those lines, or are they adjustable from the
On the AC-45, they're only adjustable by going out to the wing.
And so do they do that in the tack, or do
So they do it, yeah, right, or just send somebody down to do it. Yeah, the main control that you actually play is the travel. So that does it.
It looked like there was only one twist control line. Does that mean you've already set up a preset ratio for the offset of the elements?
That's right. On the AC-45, that triangular quadrant, because the different control lines come in at different distances from the pivot, they get a different amount of adjustment. So it lets off the top controls much more than the bottom ones, for example. So that's why you get more twist motion at the top. So it's sort of the motion of that control at the bottom sort of mirrors the twist distribution you get up all down the wing. Now, for the AC-72s, you can expect that they'll have a much more sophisticated control system, and they'll be able to perhaps vary the twist along the span of the wing. The AC-45 was designed to be a very simple, sort of a seat-of-the-pants kind of boat. The only instrumentation on the boat is the GPS speed. And so, they're designed as essentially trainers to get the crews to get a feel for what it's like to sail with a wing. And so we wanted a system that was fairly rugged and simple enough that they didn't get distracted by trying to do a lot of fine tuning. Yeah.
Talk a little about the sailing directly upwind and faster than the true wind and all that business.
Okay, well that's of course quite a different craft. Although these boats can sail upwind and have a BMG faster than the wind, and they can sail downwind at the 45 is about twice the speed of the wind, and USA 17 at 3 times the wind. So to give you an idea what that's like, if you were to release a hot air balloon from the windward mark at the start of the race for USA 17, it could actually beat the balloon back to the finish. So the time it takes the balloon to float down at wind speed from the windward mark to the finish, USA 17 could have sailed up to the windward mark and then sailed back down and caught it at the finish. For the craft that sailed faster than the wind, it had a rotor, a propeller, and that went with a chain drive to the wheels. And so it could work, you know, facing directly into the wind and downwind. When it went upwind, the propeller acted like a windmill. So the wind turned the propeller, the chain drive turned the wheels, and that drove the craft. When it went downwind, it was the reverse. The wheels drove the propeller, and the propeller propelled the yacht. And that's why when it went through the wind speed and had zero apparent wind, it was still able to accelerate, because it was actually the rotor acting as a propeller, just like taxiing an airplane on a calm day will propel the airplane. That's what was propelling the yacht downwind.
Yeah. Do you see any applicability of the wing sails to either production vessels or monohulls?
There's no reason they couldn't be used on a monohull. All of the wings have higher performance. They're a bit of a logistical problem, because you need to sort of fly a wing 100% of the time. Now, we found that the AC-45s live quite comfortably on a mooring. I don't know any other, certainly the C-Class never leave their boats on a mooring. Now, land yachts use dollies, where the wheels of the dollies have axles that point at the front wheel of the land yacht. So it can swing about the front wheel as though it's on a mooring. And they live quite happily that way. And that was sort of also sort of the origin of the dollies that we use for the AC-45s, so that we can move them around while keeping the boat always facing into the wind. The big problem with the wing sail is you can't reef it. And so I don't think that they'll ever be very useful for offshore, simply because you know, there are times that you just can't stand that much area up. And so I think for course racing like this, for speed records, things like that, I think they're the right choice, but I don't think they're the right choice for offshore. Kim.
We understand that a 3-element wing develops more power than a 2-element wing. Can it also be depowered more effectively?
Yeah, there's really not a lot of difference between the two. There's sort of a difference in terminology too. The C-Class talked about 3 elements meaning 3 moving pieces. And in the aeronautical parlance, 3 elements would always have 2 slots. But basically, the middle element is typically slave to the flap. So from a practical standpoint, in terms of sailing, it's just like a wing that only has 2 elements. And you just simply move the, you know, one camera control or the flap control, and that does it all. The middle element, like the tab in what I've shown you, is really kind of a fine-tuning device. What you find is that when you close down the slot with a tab, it shifts the load from the flap to the main element. And when you open it up, it shifts the load from the main element to the flap. The total lift doesn't change very much, and surprisingly, the drag doesn't necessarily change that much. But the moment changes quite a bit. There are, you know, sort of parts where the tab can make a small difference in terms of the performance, but it's not a real big actor.
What is known about the day in Valencia when the Artemis wing came tumbling down?
I don't know. All I know is what's in the press. I don't know that even within the team we've heard much in the way of rumors as to why they broke their wing.
The wing can sail at about 20 degrees to the wind. The soft sails are still set at 30 plus degrees to the wind. Has there been any development in bringing the soft sails being able to? Because after about 6 knots, the soft sail becomes a near break on the performance. But I believe under the rules, you've got to have a soft sail up all the time.
Again, the rules are there more for to make the racing as equitable as possible, and at this stage, we want good close racing between the boats, and don't necessarily want to see huge differences. Now, in the last America's Cup, what you saw with USA 17 was there was a crossover wind speed where it was faster with the soft sail below that wind speed and faster without the sail as wind speed picked up. And the first leg of the first race is a good example. They started off with a jib, and then once they went past that crossover, they dropped it, and they were sailing with wing alone. And in fact, the wing had been originally designed to be sailed wing alone. And then they rolled out the Denneker for the off-wind leg. So, it depends on the details of the design as to whether it's going to be faster with a soft sail or not.
Thinking about laminar flows, wondering, is there anything more to be said about the development of coatings? There was reference to the clear plastic and the Kevlar caps, but is there anything more in your mind in coatings?
Coatings are not going to really help you with laminar flow. What you need is a smooth surface, as smooth as possible. You're talking about roughnesses under, say, 1/10 of a millimeter, which means that the branding graphics they put on these wings is right at the limit of what you could tolerate. But the air that actually touches the surface doesn't move, and so it doesn't matter very much what that is. Now, for the turbulent boundary layer, if you had a groove surface like the riblets that Dennis Connors used on Stars and Stripes in Fremantle, what those do is they're sort of a texture that's at the same scale as the small turbulent eddies in the boundary layer. And so they reduce the turbulent skin friction by essentially keeping those eddies away from the surface and by increasing their damping so they don't persist as long. But those are also prohibited under the design rules, so it's kind of a moot point. Yeah.
At 20 knots of true wind, what's the speed difference you anticipate between the 45s and 72s?
The 45s have been up to a little over 30 knots, and I would expect that the 72s will probably hit speeds probably more like 40 knots, perhaps above. Yes.
I noticed that the hulls are diving a lot, but they're making a turn. Why don't you have a tab in the front to hold the bow?
Well, people have tried various planes and other things in the bow to hold the bow up, and they've never really been all that successful. One of the problems is they only work in a comparatively narrow angle range, and once you go past that, they actually drive the bow down. So it's better to simply design with enough reserve buoyancy up front rather than put planes or other surfaces to try to keep out. And the other problem is the pitchfork problem is worse at low speed, and that's when those things are least effective. There's a question back here? Okay.
As far as the twist, it was a breakthrough to be able to control the twist. Was that for drag?
Yeah, for drag. Computational was the first C-class to be able to do that, to twist their main element. And the problem is that, of course, the apparent wind angle is different between the bottom and the top. You have basically a narrower apparent wind angle at the bottom than you do at the top. So you'd like to have you'd like to have that main element angle the same relative to the apparent wind angle. And the other thing is if you use just the flap, you change the lift up and down the span. You can achieve the same lift distribution and the same induced drag, but you are flattening the top, and that may not be what you want. You may have wanted the top to be cambered up more. So, well, or just to optimize the performance, to minimize the parasite drag. But at the same time, the way you achieve that twisting main element is you basically have sort of a spar within the wing. So you have You have perhaps a round or elliptical spar, and then you have the shell around it that forms the aerodynamic shape of the main element. And then those are tied together, say, at the top, so at the bottom you can rotate them relative to each other to get the twist. And so your spar becomes smaller than it otherwise would be if the shell itself was your structural element. So the wing is not as stiff, or else it has to be heavier. And even if you give up some stiffness, it'll probably still be heavier. And so, which is the better trade-off? Is it better to have, a lighter, stiffer spar, or to go with that little bit of extra aerodynamic efficiency?
On the glider technology today, they're putting vibrations into the wing to actually disturb the drag on the end of it. Do you think that technology would eventually end up being used here, and do you think it would be any benefit?
Well, on the gliders, gliders are designed to maintain extensive amounts of laminar flow in their bonder layer. As much as 60 or 70% of the wing chord could be laminar on a glider. They operate at similar Reynolds number. In other words, a combination of speed and size that we operate in. But the difference is they're operating at an altitude where the wind is calm. You may have the wind blowing, but you don't have the turbulence in the atmosphere that you do because the atmosphere is close to the surface and coming through the Golden Gate and things like that. So I think it's an open question right now as to whether or not there is so much turbulence in the air at the altitude that we operate that there's already enough to trip the flow to turbulent in the bond layer, or whether you can achieve laminar flow. And I think that's something that needs some study, and I don't think anybody really knows the answer to that right now. Yes, sir?
Yep. Are you using any supercritical finite elements in the design?
We're using a great amount of finite element analysis, and every part of the boat is designed using finite element analyses. There's about, I think there's about 20 people total on the Oracle design team. Of that, there's, I think, about 6 or 7 that are sort of aerodynamics, hydrodynamics, and another 6 or 7 that are devoted solely to, or more, I would say, devoted to the structural design. And and they use finite element analysis as their daily tool.
And how about the supercritical wing elements NASA?
Yeah, a supercritical wing in aircraft is one which is designed to delay the formation of shock waves at transonic speeds. And we're not going quite that fast. We're working on it. We've got a ways to go. However, where that is applicable is to the foil, because the way you make a supercritical airfoil is you basically limit the maximum velocity on the airfoil, and because you're trying to stay underneath that sonic limit. And we have a similar problem with the foils, because when the velocity gets to be past a certain point, the water literally boils because the pressure has dropped so low. And that's called cavitation. And these boats definitely go fast enough to cavitate the foil. And so you end up with a similar kind of design where you're trying to make basically a flat pressure distribution that's just underneath that limit. And so you see the cross-section shapes of the foils in these boats looking very much like a supercritical wing on an aircraft.
The wings on the AC-45s are all one design, is that correct?
That's correct.
And we can see some difference in jib design and Jenniker design from the
That's
different
right.
boats. Can you
That's
explain?
right. So the teams provide their own jibs and Jennekers. There are some, there are limits in terms of area, but they're pretty much allowed to design their own. So this gives some design aspects to the AC-45, and it also means that we don't have to try to vigorously enforce a one design limits on sales because sails are constantly needing to be recaught and so forth. And so yeah, it also helps get the teams up to running on how to design sails for these kinds of boats.
Are you doing any work on the center boards? And so can you tell us anything that you're doing on for the big boats?
I personally haven't been working in that area of the boat. There, we have an engineer, his name is Michel Kermerer, who is one of the wise old men in this field, and he's been doing a fantastic amount of work on designing the foils for our AC-72. And no, I can't tell you what they're going to do.
Why don't we take two more questions here? Take two more.
What does it weigh, and how do you think about weight?
Oh boy, I'd have to look it up. I don't know exactly what the weights are on that.
How does weight impact design?
About a ton.
In the 72 rule, there is a minimum weight for the hulls and a maximum weight. So, so the weights are, fairly narrowly controlled on that boat, but I just don't have the numbers right off the top of my head.
The design team, what percent of the resources allocated to wing and above the water, what percent to hull?
Oh, our design team, we've got, probably, I'm thinking 3 or 4 guys that are doing most of the structural design on the wing. Comparable number working structural design for the platform. In the aerohydrodynamics, we've got one guy that's doing all the hydrodynamic calculations, and others doing the foil design, and another naval architect doing the hull design. So it's kind of even, I would say, between the hull, platform, and wings. And then there are also guys who are working the mechanical design of all the systems, the hydraulics, the winches, all the stuff that the sailors need to do. Okay, so upwind, you're limited by the heeling moment of the boat, and so you're tending to sail flatter and with more twist in the wing. And then downwind, you're trying to camber up more to get more power. It kind of depends on the wind range too, because in light winds you need everything you can get to keep the hull flying in light winds compared to upwind. So it's just like on a soft sail boat. You upwind, you flatten and trim in tighter, and downwind your trim is freer and you ease the outhaul to camber up more.
Along the same lines, the upwind and downwind, this is going back to a long time with me. And your rig and downwind, you're trying to get drag.
On these boats, you're always sailing sort of in the upwind mode from that standpoint. You're never trying to get drag. These boats never have a parachute when they're going downwind because the wind is always coming from ahead of the beam. So you're looking for efficiency both upwind.
I think this is probably a good place to leave it. Before we shut down and start thinking about race 1 and 205, we have with us today a man who in 1977 played a tactician role at Rhode Island South, caught a couple lucky ships, and managed to help Ted Turner win the America's Cup. Gary Jobson, please stand up. We've done a few other things from time to time, but we're always glad to have you here, Gary. And Tom, this was fantastic. We thank you so much.